let's move on here to the subject matter of today, which is distance. What the hell is distance? But before we get to distance, let me cover an issue that was left behind. I asked a person to answer some questions related to one-way mirrors, and I didn't get an answer this time either, and I lost hope of getting an answer. Fellow says, if laser pointer, right, used from a dim side, it shows up on the brighter side. Yeah, we know that. We all know that. I mean, that's he's just repeating stuff that's not being asked. When the lighting is correct on both sides for the half silver glass two-way mirror illusion to work. Yeah, we understand that too. That's a description. You haven't explained anything. These effects have nothing to do with anything else besides half silvering method. And again, he didn't answer the question. So after 5 times, I throw in the towel. I don't think the guy has an answer. He's just walking around the issues. Okay. The question was very clear. I think I made it clear in the last 2 times at least. And if he doesn't answer, it's because he doesn't have any clue. That's why it is. Okay, so let's get into that. Let's find out what the problem is. Okay, and the problem starts there, where we have a man looking at a mirror, and the woman behind the glass. She sees him, but he doesn't see her. He sees his reflection in the mirror. She doesn't see him. The question is, does light go both ways? Why does light go to her eyes, but her light doesn't go to his eyes? This fellow keeps insisting it's got to do with something with the coating on the mirror and something to do with the lighting in the room. And the answer is no. Quantum mechanics doesn't say that. And that's the question we've got. The question before us is, what does quantum mechanics say? Quantum mechanics does not deal with lighting in the room. That's classical mechanics. Okay? Quantum mechanics deals with what happens between the photon and the electron, which is a component of an atom. So here we're talking about subatomic interaction. That's what quantum deals with. That's what quantum tries to answer. And we need to find out, what does quantum say about this situation? And you won't find in quantum mechanics anything about the lighting in the room. It's got to do with something totally different. The issue is whether the electron absorbs a photon or it doesn't. That's what it's got to do with. So this fellow, for the 5th time, did not answer that question. He just eludes the question because he doesn't have an answer. Okay, that's the only issue. Okay, so let's look at, this is the quantum version here. Okay, we have 2 situations. One is opaque and the other one is transparent according to quantum mechanics. Okay, so I want to make that clear. This is quantum mechanics. This is how quantum mechanics answers that question. It says, okay, what is opaque? Well, opaque means that an electron gets, or energy, whatever you want to, photon or energy is absorbed by an electron. If the photon has enough energy, whatever that is, okay, Feynman says he doesn't know what energy is, okay. If it has enough energy, it boosts the electron to a higher energy level, which is a situation on the top. So because the photon is absorbed, because the energy is absorbed, it doesn't continue to your eye. Okay, that's what quantum says. And what is transparency? Well, more or less the same thing. The photon does interact with the electron. But there's 2 possibilities. One is that it delivers the energy, not sufficient energy, but enough energy for it to vibrate and pass that energy, whatever energy is, to another atom or another molecule or whatever next to it, a neighbor. And so it passes it off as heat. The other option is that it hits the photon. The photon doesn't like it because it says, well, you're too weak. You don't have enough energy to boost me to the higher energy level. So it lets it go by or spits it out, one of the 2. Okay? So what happens is there is an interaction of some kind, but that interaction is not sufficient energy to boost the electron to a higher energy level. Okay, so those are the explanations of quantum mechanics. So what does quantum mechanics say about what's happening in this situation, okay, in the one-way mirror? Well, quantum mechanics says that light actually travels in both directions. Okay, that's what quantum says. But in one direction, it's absorbed, in the other, it goes through. It's like you have holes and brick walls, holes in brick walls. So the photon hits a brick wall and it gets absorbed or reflects or whatever. And when it goes through a hole, it just goes all the way through to the other side. That's what quantum says. Okay, that's the version of quantum. That's the one we have to address. Okay, none of this classical stuff saying, oh, the lighting in the room, oh, the coating on the mirror. No, none of that has anything to do with the quantum version. Okay, and I think I made that plain, and fellow just alluded to the question. Okay, and so here we have it, a different version of the same thing. Here's opacity. This is what an opaque substance would do. You have that green energy arrow. Okay, it absorbs, the electron absorbs that energy and jumps to a higher energy level. Then it releases it back, maybe through reflection or heat, and it falls to a lower energy level. Okay, this is the quantum version. Okay, of opacity. This is opaque. Here's transparency. Okay, in here in this case, the photon just goes through, but it does interact with that little electron ball. Okay, I should have put it in there in such a way that it touches the electron ball to make that planar. Okay, but I didn't do that. But just think of it. That green arrow hits the electron ball, that red ball that's going around, but it doesn't have enough energy to hit it to the higher energy level. So the electron just keeps rolling allegedly along the same orbital, or that orbital where it's going around, or energy level. So this is how quantum mechanics answers these questions. Okay, so this is opacity and transparency according to quantum mechanics. Okay, let's put them side by side so that we don't lose track. Okay, or up and down. Okay, just so you can compare. I want you to understand the quantum version. This is the quantum version. Okay, case of transparency, the photon goes through. So if you have glass, SiO2, as part of remember the coating on the mirror, on a one-way mirror, is very light. And what do you mean by that? Well, what we mean is that when it hits like aluminum or silver, whatever coating it's got on there, it's going to hit that brick wall, and it's going to be opaque, like shown on the bottom. Okay, if it hits the area where there's glass, SiO2, well, in that case, it goes through according to quantum mechanics. But how does it go through? It goes through a little relay mechanism where the photon gets absorbed by the electron. Well, not absorbed, but the photon touches the electron and says, no, you're weak, we'll let you go by. So it goes by, it has to interact, because otherwise, how does the electron know it's weak or not? So there's got to be a gazillionths of a second interaction. Then the photon moves on to the next atom, then moves on to the next atom, then moves on to the next atom, and comes out the other side. That's what quantum mechanics says. That's the mechanism quantum mechanics proposes. Okay, so I want you to understand the mechanism first. Okay, so it's got nothing to do with the lighting in the room. It's got to do with the fact that the photon will go completely through. Okay, and in the other case, it gets absorbed. That's what it's got to do with, according to quantum. Okay, so here's a comparison between the two. Okay, the one on the left would be the fellow, and the one on the right would be the gal who could see the fellow. Okay. And if you have an atom that is either silver or whatever the coating is made out of, it's going to be opaque. And so it's going to absorb the electron coming from the left. That's the upper one on the left. And even if from the gal's side, if there's a photon coming from the right, from her side, it's going to be absorbed by one of these silver atoms. And we're just putting atom. We're not even going to deal with molecules. We just want to look at the process here. Okay, it's absorbed by an electron of one of those atoms. What happens under transparency? Well, you can see there, it's a relay race, okay? This is the mechanism that quantum mechanics proposes. You have a photon coming from the left, okay? It's going to be absorbed momentarily, or it touches an electron, then continues to the next one because it doesn't have enough energy to boost it to a higher energy level, and it goes to the next one, to the next one, to the next one. It's kind of like a relay race where they're passing the baton to each one until it comes out the other side. This is transparency. So in one case, the photon is absorbed. In the other one, it's allowed to go through. That's the mechanism quantum mechanics proposes. Okay? And so what I want to do next, I want to compare quantum against the rope model. Okay? So you can see black and white, yes or no, on or off, one against the other. And here it is, the rope model. Okay? All the atoms are interconnected by ropes, electromagnetic ropes. You have the laser, high frequency beam come from the left here. And what happens is you have that high frequency, it boosts the pumping speed of the atom, which then transfers that same pumping speed to the next atom and so on down the line. It's a relay race, but it's done all through this rope. Okay, and compare that against the Ptolemaic mechanism that quantum mechanics proposes, where the photon is touching at least the electron. It has to touch it at least once, and then continue on to the next atom against the next atom and so on down the line. Okay, so it's up to you to figure out which one you would choose to be efficient. Which one does Mother Nature use? Okay, does it use this rope model, or does it use this discrete particle model? That's the issue you got to ponder. Okay, moving on here. So let's go back to distance. In order to talk about distance, we really got to start at the beginning, more or less. I can't say the beginning. We never started at the beginning. Even the universe had no beginning, except in the religion of general relativity. In science, no, the universe had no beginning, meaning matter was not created by God or by Big Bang. Matter was always there. Okay, Matter cannot convert into space. Space cannot convert into matter. Therefore, an atom cannot turn into empty space, into nothing spontaneously for no reason whatsoever, without cause, without mechanism, and vice versa. Space cannot suddenly pop into and become an atom or whatever. So matter has always been there. Okay, and that's under the rope model. Okay, matter has no way of disappearing or being created. Okay, like in the religion of general relativity. Okay, but about 400 years ago, we're talking about here the 17th century, so-called 17th century revolution. That's when science began to change a little bit. And what changed? Well, we remember people like Galileo and Newton, maybe Leibniz, Huygens, and some of the other luminaries of those days, but they weren't really the first. Okay, they came like a generation, at least Galileo came more or less a generation later, maybe 20 years, not even 20, maybe 30, 10 years later. But Newton for sure came a lot later than, Newton was born the year that Galileo died. So he was a generation even further removed. The people who came before that were people like William Gilbert and Gilbert and what's the other guy? Yeah, I'm here, Francis Bacon, sorry. And here's William Gilbert. What did he do for science? Well, not much, but he played around with magnets. And he wrote this book, De Magnete, meaning on the magnet. He was writing a treatise on the magnet. And he toyed around with the magnet, and what did he do for mankind? Well, maybe one thing only, and I'm not even sure he was the first one, but at least in the West he was. And what he said is that the Earth is a magnet. And he playing around with magnets is what led him to this idea. And what I'm trying to say here is that, he was one of the first to start doing experiments. Okay, and that's how experiments kind of entered into science, because before that it was all thinking, pondering, imagining, visualizing. And they're trying to figure out how this universe worked, and they couldn't figure it out. And these people started saying, well, why don't we do some experiments? And, this was one of the first guys to do experiments. He did it with magnets. A fellow in Spain, Francisco Sanchez. And he was a philosopher, as they call him. And he said the following, and you can see how the mind is changing at the beginning of the 17th century, 1600s, early 1600s. Says the search for causes quickly descends into an infinite regress, and so cannot give certitude. He started questioning, whether Aristotle was, the Greeks in general, were they doing the right thing? Okay? And he says syllogisms are circular. The syllogism started with the Greeks, and do not add to knowledge. Okay, so he starts questioning. Perfect knowledge, if attainable, is the intuitive apprehension of each individual thing. Okay, but science, perfect knowledge of an individual thing, is beyond human capabilities because of the nature of objects and the nature of man. The limitations and variability of man's senses restrict him to knowledge of appearances, never of real substances. And I don't know if you figured it out. You probably didn't, because nobody has to this day until my book came along. And I'm not bragging here, I'm just stating the fact, okay? And that's that nobody figured out that you don't do experiments to figure out anything about light, magnetism, gravity, because you can't see or touch the mediators Mother Nature uses. So he didn't really specify exactly what meant by what he meant by all this, okay? He just says, because of the nature of objects. Well, what do you mean by that? Why would you do an experiment, for example, why would you go to the lab if you can't see or touch the objects that Mother Nature uses to do all her magical phenomena, such as gravity and magnetism? You're going to go to the lab. What for? All you need is one experiment, like I say, to talk about gravity. And here it is. This is the only experiment you ever need to do. You let go of the pen, it falls to the floor, to the center of the earth or whatever. Never falls to the ceiling. We're done. Now explain it. And you can't explain it until... certainly you're not going to explain it with math. Math can only describe. The only way you're going to explain it, the mechanism, is by visualizing, by introducing, by making visible the invisible objects that Mother Nature uses as mediators. So there's something here that's either pushing from above or pulling from below. But something had better come in contact with a pen, with the skin of the pen, because otherwise you're introducing spirits, black magic into your theory. You're saying nothing touched this at all. Nothing came in contact with this, but it was always pulled to the floor. Like if the pen knew it's got to fall downwards and not upwards. So nothing came in contact with the pen. Why? Because you can't see or touch it? Is that why you say nothing came in contact with the pen? Okay, so this is the issue. Yeah, it had to do with the nature of objects. And so what these people did was move in two directions: experiments and math, neither of which have anything to do with science. Science is not descriptions, mathematical or otherwise. Science is not running an experiment. You can run an experiment and not understand absolutely anything. You can study all week and not pass the test on Friday. So why did you study? Because you studied, you're a scientist? Because you did an experiment, you're a scientist? Because you did some math, you're a scientist? No, you're a scientist if you can explain something in a rational manner. You can explain, especially in the case of physics, a mechanism. Then you're a scientist. Now you become a scientist because now you're using your gray matter up there in the attic. Okay, so this is the issue. And so what happened was all these people, because of these original pioneers of science, they started taking the causes that they had in the old days. In fact, I think I have it here with Francis Bacon. Give me a second here. He still was thinking of causes, okay, in his Novum Organum, okay. He said, he presented his method, his new method for science. He said, look, we got to forget about the Greeks. And instead, we got to look at this other thing. And he says, he starts it with his three main steps. He says, a description of the facts, a tabulation or classification of those facts into three categories: instances of the presence of the characteristic under investigation, instances of its absence, or instances of its presence in varying degrees. And then the rejection of whatever appears in the light of these tables, not to be connected with the phenomenon under investigation, and the determination of what is connected with it. So he was saying, look, we run an experiment, let's look at what happens, and based on what we observe, right? So we have observation and experiment. That's what we're going to draw some conclusions out of. Not out of this stuff that Aristotle says, that, like he says, a bigger stone will fall faster than a lighter stone because it's bigger and weighs more. So this fellow is now saying, look, what we got to do is some experiments and observe them, and from that we can reject some theories and accept others. That's essentially his method, okay? And so he presented this in 1620, which was a little sooner than Galileo. Galileo is, you have to remember that first he had his two systems of the world where he almost got in trouble with the church, and then he came up with that other system, which was he took up his old practice of playing around with mass, and he wrote some balls and so on. So he came up with some ideas on how masses behave. And Newton's going to read that later on, and he's going to give some credit to Galileo, and essentially develop from there on his descriptions, because they're not really theories. They had no theories. Theory is an explanation. None of these people explained anything. All they could do was describe. And what they what they figured out is that, masses like two different weights fall at the same speed. And they were shocked by that realization in great measure because they were taught something else in school. They were taught the Aristotelian version. And they said, well, no, that's not true. And incidentally, again, it wasn't Galileo who threw the first balls from the Tower of Pisa. Okay, so I've covered that in the past. So yeah, this was an age when they were starting to use math and experiments. And what they were leaving behind was this just explanations without any support from experiments or equations. Okay, so what they were working on, whether they knew it or not, were descriptions. Okay, they were working on descriptions, and that's not what science is about. Science is about explanations, and we're trying to figure out how this universe works. Okay, and by how, I don't mean here's the description. No, by how I mean the causes. And they tried to, up to this point, they were still trying to figure out the causes. Causes died essentially in the Roaring '20s when quantum took off, and that's when they figured out there's no way we can ever explain this. And so they stopped looking at causes. Okay, and so, or like Feynman's going to say many years later, he says, physicists have given up on that. Okay, so they don't look at causes anymore. That's considered philosophy, philosophers of science, philosophers of physics, and they don't deal with that stuff at all. They just deal with descriptions. They go to the Large Hadron Collider, or maybe throw a rocket into the moon, and they look at what happens. They measure, and they give you an equation, and that's all that mathematical physics is about. Okay, but that's not physics. Physics has to do, science especially, has to do with explanation. You have to explain how gravity works, how Mother Nature does that magic trick. You have to explain how a magnet attracts another. That's science. Okay? And these people never figured it out. Okay, Einstein didn't figure it out. Bohr didn't figure it out. None of the people since then have figured it out. Okay, so where does this take us? Well, what happens was all these people put the set the stage. You can say the foundations of physics, and the foundations of physics are all rotten to the core. Okay, for example, you won't see in any book on planet Earth, textbook of physics, you won't see the definition of the word object. And it turns out, you know what a thing is. And it turns out you can't do a physical interpretation, a mechanism, without objects. I mean, if there's absolutely nothing in the universe, if God hadn't made any material, any atoms, any nothing, what would you be staring at? You being there with God, drinking beer together, right? What would you be staring at if there's nothing there? So the first thing you need in physics is an object. You can't do physics without an object. They never figured that out. And so that's where the problem started. And why? Because mathematicians have no use for objects. They simply represent objects with point particles or point numbers, really. And they start moving the points around, giving you the idea that they're moving a physical object. And when you say, was that an object? Well, that's the center of mass. So they're moving this concept known as the center of mass around, and they forget about the elephant. Okay, so that's more or less the situation today. So here's a book that I have. Okay, this book, and it's a book that I've had for a long time. It's typically a type of book that you find in high school. In this case, it's for liberal arts in college. It's people who are not into physics per se, but they want to learn a little bit about physics, or it's maybe one of those courses they take, and they just want to get an introduction to physics. And it's a typical book for people who start doing physics. Okay, and so let's look at some of what the table of contents are here. And here you'll see, all these titles there, all these headlines. And if you look at that first group there, you'll find that it's all got to do with space, with the solar system and so on, until you get to mechanics there, page 74, okay? And what happens there is they start talking for the first time about some of what the mathematical physicists consider physics, okay? So what do they talk about? Well, if you go in there and look at that page, you'll find this. Mechanics, okay, and what do you see there? Well, in that whole chapter, these are the type of things that you find. You don't find mechanism, you don't find explanations. What you find is equations. And you say, this is mechanics? I thought mechanics was, like the guy who works on a car. He doesn't work on equations, okay? And so you go in there and you find speed equal distance divided by time. Great, that's an equation. Angular speed, velocity, acceleration, and finally force equals mass times acceleration. They're talking about motion. In all these cases, that's where it starts. That's where the so-called physics starts. Okay, and when you look at speed equal distance divided by time, well, you can say also distance is equal to time times speed, or speed times time. Okay, so you multiply those, you get distance. Okay, but that's not distance. That's what is known as distance traveled. And here you see what I'm referring to. That's distance traveled, because what they're doing is rolling out the front end of a measuring tape. Okay, is that distance? Is that the same thing as separation between two objects? Okay, so this is where the problem starts, because what they're doing is they're putting an equation. You say, well, is that distance? Speed times time. No, that's not distance. That's distance traveled, because either you're laying tiles or you're rolling out the measuring tape or you're counting seconds. What you're talking about is frames of a movie. You're talking about something in motion. Is that what distance is? Motion? Okay, so this is where the problem starts, because these people have always looked at distance as something dynamic instead of something that is static. Okay, like a separation between two things. Okay, let me get rid of this. Give me a second here. Okay, so here we look up the word distance. What does it mean? What is the definition of the word distance? And we go to the Wikipedia, it says distance is numerical measurement of how far, okay, apart objects or points are. Okay, and how are you going to find out how far? We're talking about an amount, a quantity. We're looking for a number, okay? How far? In physics, we don't care how far. In physics, there is so much separation. That's physical, okay? Between the chair and the table, there's a distance. We don't care what number distance that is. In fact, if you go to the land of the Klingons, I'm sure they're going to have different measurements. They won't have feet and meters and so on. They're probably going to have a different type of measurement. And so their how far will be different, at least numerically, right, than the how far over here. So how far is, they're talking about an amount. Okay, and that's not what distance is. Distance is separation in physics. In math, it's how far. Okay, in physics or everyday usage, distance may refer to what? Length, physical length. So in the religion of mathematical physics, distance is the same thing as length, and length is the same as distance. When you look up the word length, that's confirmed, is a measure of distance. Okay, so length and distance in the religion of math is the same thing, because what they're doing is extending the tip of a measuring tape or counting tiles. You know, you get a tile like 1 meter and you put all these tiles, say, well, this from here to there is 5 meters. Okay, so what did you do? Well, you laid a bunch of tiles and you counted how many tiles. So we're talking about not distance, we're talking about distance traveled. How many steps, how many tiles you put from one end to the other, or how far the distance from the time the runner started to the time the runner ended. What was the distance? Well, let's roll the measuring tape, again, the front end of the measuring tape all the way and measure and get a number, get a unit. That's what that means in mathematics. In science, physics, okay, something different. We can't use that for explanations. That's good for descriptions. It's not good for explanations. In science, we have to explain. In order to explain, we need qualitative stuff. So we look at separation, gap, chasm, okay? And when you look at the dictionary.com, it's got maybe a little better one, but again, they talk about amount of space between two things, points, lines. If they would have left that part out and just say space between two things, then they would have the definition of physics, more or less, okay? Space between two things, that's what distance is, okay? And again, the state of being far apart, okay? Those are the notions of physics. So they're irreconcilable between math and physics, okay? So we distinguish what mathematical physics does, and physics is a big word, I'd rather call it mathemagics, with what we do in physics. In physics, we don't use amounts, we don't use units. We don't care about that because those are descriptions. We're not going to use them at all. What we're going to use in physics is separation. That's what's going to be distance. And we need that separation to define the word location, which again is a static qualitative concept. Okay, it's not, location is not the position of mathematics. Position, again, is motion. No such thing as position in mathematics in the sense of what people think of position, like I'm at this position. That's not what it means in mathematics. In mathematics, position is an ordered pair. That's what position is. Okay, so it's motion. You got to go 10 feet this way and 10 feet that way, and now you arrive at the position. Position is unrolling the measuring tape also. Everything in mathematics is dynamic. There's no static concept because mathematics has no use for static concepts. Okay, so how do we define it in science? Here's a definition of physics of distance in physics. Okay, here we have it. Distance is what lies between lengths. Length is what a box has, a table has, a thing has, from one side of the box to the other side of the box, for example. Distance is the separation between two boxes, between two objects. So we summarize and say distance is what lies between lengths. That's the synthetic way of putting that. Okay. A little different than the notion of unrolling measuring tapes or counting seconds on a clock or whatever. All that has to do with math. It has nothing to do with physics. Okay, here we have why that's important. Okay, why it's important to distinguish between the static distance of physics, the separation, and the so-called distance, which is actually distance traveled of mathematics. Okay, there's difference, and here you can see it in the equations that Newton came up with. They give him credit. I'm not sure he never wrote these equations. Those equations were essentially written by French. Later on, they took it out of his book, the notions, the concepts, and they turned them into equations. But that's, just academic. That's history. Whichever one you believe, it's your problem. The issue is the following. We're going to assign them to Newton. Okay, we're going to say that we have the gravitational equation. Okay, and the distance there is different than the distance in his dynamic distance, as I call it, the force equals mass times acceleration, his second law. And what do we see there? Well, we see there's two different kinds of distance. The distance in the gravitational equation is the distance of physics, separation. That's what it is. It's a static concept, that distance. So we're distance squared. And the other one is a dynamic distance. Okay, so these two distances are not the same qualitatively. That's what I'm saying. Okay, and what are the differences? Well, distance is static in the case of the gravitational equation. In other words, the distance squared, that's in the denominator of the gravitational equation. The other one is dynamic. Okay, in the first case, the one on the left, distance is between two objects. The distance traveled of the second one is distance from the starting point of the object to where you measure. So you're measuring a single object. You're saying this is the starting point, this is the ending point. That's a different distance than distance between two objects. Okay, separation between two objects. Each frame in the movie depicts a static distance, and the other one has an itinerary. Distance is towards the other object, and here it's the distance away from its starting point. You can, even if you put an object there, you're talking about an increasing distance. Okay, that's the distance of Newton's second law. Distance is a measure of weight in the case of the gravitational equation. In the other case, it's a measure of velocity. And then force increases when distance decreases in the case of Newton's gravitational law. In the other case, it's force increases when distance increases. So there are differences, qualitative differences in these two types of distances. Okay, and you say, well, what's the bottom line? Why is this important? Okay, and here let me show you why it's important. One thing Einstein couldn't figure out was his principle of equivalence. He couldn't figure out the cause, how Mother Nature does that magic trick that this equation can be equal to that equation. And here you see it. Okay, we have one atom belonging to one elephant. So we're going to have one hydrogen atom only. That's all we're going to look at here. And this hydrogen atom belongs to an elephant. The elephant could be falling to Earth, or maybe the elephant is flying away from Earth. Okay, and so what we're saying is that a given location, that elephant, that atom has a specific weight. If that atom changes position, location, right? If it's farther away or closer to the Earth, it automatically has a different weight. Okay, so if you're standing close to the Earth, you weigh different than if you're out in outer space with respect to the Earth, and so on down the line. Okay. So what's the issue here? The issue is that it doesn't matter if the elephant is flying out or coming towards the Earth. That atom at a given location, okay, has the same value, whether it's force equals mass times acceleration or force equals to the Newtonian gravitational equation there. Okay, that's the issue. Why? Because under the rope model, every atom there, in other words, in this case, this hydrogen atom, is connected to every atom on Earth. And it has a certain number of ropes converging upon it at that distance from the Earth. That's why the principle of equivalence, the underlying cause that for the principle of equivalence. And of course, under mathematical physics, mathematics, you cannot explain it because all they have is equations. They have no idea what's causing all this. They have not figured out that all these atoms could be interconnected. Okay, that's where the problem is. That's where the problem starts. They simply think that what they're staring at is just the hydrogen atom and the elephant. They say, well, why is in some cases under these circumstances force equals mass times acceleration the same as the other one? Why are they equal? And what they do is measurement. They say, well, they're very, very equal. Yeah, no kidding. Because the number of ropes converging upon that atom at that distance is the same, irrespective of whether that atom belongs to a feather or an elephant. Okay. Okay, so that's in a nutshell why distance is important from a qualitative point of view. You need to determine whether you're talking about distance traveled or distance, separation. And in physics, we deal with distance, meaning separation. We don't deal with distance traveled. In other words, we don't care about units and we don't care about amounts because those are just descriptions. And those cloud, if anything, our understanding rather than enlighten us. What we need to figure out what invisible objects Mother Nature uses to produce these effects. That's what physics is about.